And I've been working in the Cryogenics group for quite a number of years now. And one of the things that we always try and do whenever we do a project is to always kind of look at things and say, what's worked in the past? Where have we had our problems? You know, where can we do better? Those sorts of questions. Rouse and Dan are very good at making us answer those kind of questions. And this is not a comprehensive talk. All that this is basically the hitting of a few topics, areas where we've seen problems over the years. And you know, one of the things that we're trying to do is not necessarily make everybody a technical expert, but we're trying to make people do a couple things. One is when you go to reviews or you're looking at documentation from a vendor on something, you should be asking questions the whole time you're looking at the stuff. It shouldn't be, I've seen this before, it works okay, let's just duplicate it. You should constantly be trying to, you know, see what you can do to make things better the next time. And in cryogenics, for us, it deals a lot with a couple of areas. One is we don't like getting called in the middle of the night, so we tend to try and make our systems as robust as possible. We look for those weak components and stuff that causes problems. And when we get involved with the A&Es at the beginning of a project, we're going to build, like, for example, the additions onto 12JLab or with the S&S project. We even get involved early and we say, here's the kind of things we like to see in the power system. Because, you know, power going off is a killer for us because it shuts down all of the cryo equipment. It takes multiple shifts to get stuff like that back up, and it just kills us. And so we spend a lot of time in those areas. And some of this, my talk doesn't have any formulas in it like Rouse or any of that kind of stuff. It's basically a, you know, a discussion sort of thing. And these are some of the areas we've seen problems and some of the things we do to try and encourage us to not have problems. Anyway. So the topics I'm going to cover are a little bit on power distribution, and then a little bit on control system architecture, a couple of specific cryogenic sensor installations, and then talk a little bit about power conductors in a vacuum, and a little bit on some areas that we would like to see a little bit more research done. Okay, now a lot of these statements are kind of, you know, apple pie and mother kind of statements, but each one is tied to things that we've had problems with in the past. And so, you know, when you go to a place like, for example, S&S or whatever, we like to see redundant power feeds coming into the site. That's one of the things we haven't had here at JLab in the past, but we're actually working toward potentially getting a second substation now for this reason. Because what it allows you to do is, you know, if you have problems with one of your subs, you can power from either one, at least enough of power to keep, for example, the cryogenics equipment running, and which is what keeps all the helium in the tank. And, you know, if you size things properly and you install them properly, it may even allow you to continue accelerator operations. And this is something where we kind of got involved with at the bottom line, at the baseline with, for example, with S&S, because we really like to see, you know, things like dual unit substations feeding a common bus. Now I'm going to list a few things. And what I'll do in my talk is I'll list a few things and then I have sort of a graphic image that might explain things a little better. So look at two routes around the axle. But we like to see things like dual substations feeding common buses. And we like to use things that are that's called this loop power feed that we like to see for substations. And I'll talk a little bit more about that. But these are things that give you a lot of robustness to your system. It allows you to feed power to substations via multiple routes. If something should happen to an underground conductor or a disconnect somewhere, those sorts of things. And these are all, like I said, really, really important things because, you know, when you develop problems in your power system, it can just kill you. And y'all remember back, for example, after Hurricane Isabel, we basically, you know, all of the helium that was in the tunnel, the entire inventory was lost. And that was, for the most part, due to loss of power. And it took several days for the power to be restored back to the lab because of trees and other problems that were, you know, on the power feeds into the site. And I'm not saying it's 100% foolproof, but had there been more than one way of getting power to the site, we may have been able to work a little bit better. Anyway, We also like to see things like when you're powering up your 480 equipment, it's real good if you can separate your three-phase 480 power for equipment, and then from a separate feed do all your non-sensible stuff like lights and heat in the building, air conditioners, that sort of stuff. Because it'll be those things that will shut down in the middle of the night, and air conditioning system's going to shut down and take down part of your equipment if it's not, if the breakers aren't set up properly and things like that, which I'll talk about a little bit later. Just to kind of give you a picturesque view of this, what I'm talking about is where if you had multiple main subs feeding into a common switch where you can loop feed, and this is a loop feed process right here. And what it means is, for example, if you're looking at the 4160 substations at CHL right now, you can feed power either this way to these two substations and open that one if you have a problem here, or you can feed power this way and open this one if you have a problem here. And this is a similar scheme to what exists, for example, out at S&S. And you may never need this, but the one time you do, it'll be worth its weight in gold. The other thing that we do is, for example, we'll have all of our main compressors in the CHL or on a common bus like this, and we can feed power from either or both of these substations to that bus. And that allows us to do things like, let's say that plant services had to have a contractor come in and do maintenance on this substation. We can disconnect it here and here. They can provide maintenance while we're still operating the main compressors. This is what we're going to have on CHL2. Currently, on the system we have right now, there are no switches in this location. And so if they got full maintenance on one substation, we have to shut down both of them in order to not backfeed power from this bus into them. And that's very painful. We've had several instances where we've had to shut down the entire CHL just to do maintenance on these types of substations. And the same thing goes for the 480 circuit. If we have multiple subs with ways of disconnecting them, then it allows you to go in and continue operating without having to shut down for these types of maintenance activities. And so if you ever get involved in planning something or you're looking at something, these are some of the things that you need to kind of think about. Because the A&Es, they will come in and they will design you a power system. We need to get power from here to here. But they don't all the time constantly think about, well, how are you going to perform maintenance? How many downs can you survive? That sort of thing. Okay, another thing, which is a big area that can cause a lot of trouble. And this is not only in cryogenic systems, but it can also cause a lot of trouble for other systems. And that is, there's this idea of breaker coordination, which some people are very familiar with and some people have never heard of it. And what it means essentially is each breaker, as you take it out of its package and put it into a panel, it has a curve. And it may have adjustments on there where you can vary the curve to make it trip faster or slower, or you can increase or decrease the amount of current that it takes to trip at different times. And if you don't plan those out, what can happen is you can end up having a situation like we've seen around here every once in a while. That is where like a 2 horsepower or 3 horsepower air compressor pump down in one end of the LINAC will take out a main distribution panel and shut down half of the LINAC because a motor on an air compressor shut down. And we've really gone through a lot of activity over the last 5-6 years to try and really look at those things and try and do away with those problems. And what I mean by that is if you look at kind of a typical setup here, you've got like a motor or some load, you've got a breaker that's in a panel right above that, you have the panel breaker that's just above that, and there's a whole bunch of these individual breakers under this one. And then this may be fed from some main panel. And what will happen is each one of those devices has a curve. And you can vary the characteristics of this curve on a lot of breakers by changing little dials. And a lot of times what will happen is depending on who's putting the breakers in at the time they're installing them, they may either just pull it right out of the package and stick it in the panel, or they may do something like if they've seen nuisance trips in the past, they may turn the dials up once they install it into the panels. And what can happen is you always want the breaker that's closest to the load to trip. Obviously, that's a no-brainer scenario. But what can happen is, if you set these trip points along, you can actually have, like this breaker, be set, and just to explain a little bit, this is the trip current, and this is the time. So if you look at, in these areas right here, we're talking about maybe a quarter of a second type of thing. And then as you get out past that, this will be kind of like infinity. And so what will happen is the breaker will trip at, let's say, the right place, because you want the lowest one, then the next, then the next. But it may change its characteristics so that out past, say, 10 seconds. Now this breaker is going to be the one that trips whenever that motor has a problem. And that happens. That's happened around here many times over the years. And so when you're looking at installing equipment, this is one of the things that you should pay a lot of attention to. And the object is to set this breaker as low as you can to make this function properly. So again, I don't have any formulas in my talk. It's mainly this type of bread and butter stuff that people kind of tend to take for granted. I'm not going to spend a whole lot of time talking about this. This was basically a problem that we have here at JLab, and that is that in a lot of our systems, we have these legacy KMAC systems, and all these acronyms are at the end of my talk. But basically, it's a really antiquated control system that is used in a lot of places around the lab to control pieces of equipment. And you know, really, we're trying to, and a lot of the groups are trying to phase this technology out. Some groups are going to like PC 104 stuff. Some are going into VME, which is fine, but VME tends to also be very expensive. So you have to kind of look at those things. What we have been kind of zeroing in on and using in all of our control systems that we've done, for example, for SNS and for the CHL and ESR and TPF facility, is on PLCs. And the reason we use them is because they're built for industrial environments. That's what their job is. They're typically built to put into a plant, turn on, tell them what to do, and they'll just keep plumping along. And these have gotten very, very well designed now, where the failure rates are very low, and they have many, many layers of redundancy that you can buy and build into the PLC system, all the way from things like redundant power supplies that automatically kick in when another one fails, to you can actually duplicate an entire system, channel for channel. And as a problem comes on with one of them, the other system will immediately take over, and so there's no drop in service. In cryogenics, this is really important because there is nothing more frustrating than getting called in the middle of the night and have the whole plant down because one KMAC card failed or one power supply failed, that kind of stuff. Because again, it may take us 2 or 3 shifts to get our system back up and running and get beam back on target. So everything we can do to try and make our system more robust that's the sort of things that we look at.
What's the difference between the middle of the night and the middle of the day?
Well, it's just me getting called at home versus me getting called at my desk, that's all.
We don't have second shift or third shift as well.
As Ian was saying, essentially the cryogenics plants here do not have manned shifts 24 hours a day.
You're still down for 2 or 3 shifts.
We're still down for 2 or 3 shifts, yes. And that's
But it's
why
the
we
same
build
person
in
working
this
this
robustness into our systems by using some redundancy. And exactly. We'll just skip that one. That talks a little bit about PLC architecture. Okay, one of the other areas where some people might be interested in is we do a lot of temperature measurements in cryogenics. And you can go out and you can buy the most expensive sensor in the world, and if you don't install it properly, you're going to get no readings that are worthwhile. And that's really important in cryogenics, especially because we're trying to measure temperatures that are generally at very, very low levels. And so there's many things that influence those temperature readings that you would not normally see in systems that measure temperatures at higher levels. And so obviously, and again, there's some pictures coming after this, but obviously what we try to do is we try to maximize the coupling between the sensor and the fluid. Some of the temperature deltas that we're looking at are down in the 2 Kelvin region, for example, in our 2K cold box plant. We care whether it's 2 degrees or 2.5 or 2.7. And so we try to go through great lengths to make sure that we're getting really good measurements. We have installations that we do on all of our stuff as a matter of, that's our normal installation pattern where we minimize influences on any external heat that may be coming into the system. And we also, do what other people do, and that is, you don't run the signal wires near power cable. And a lot of this, although it sounds like, kind of no-brainer statements, we see problems with this all the time, even from main manufacturers of cryogenics equipment. We've had to do it where they've made errors at these times. And so mentioning it, maybe will help people kind of ask these questions when you're analyzing what a vendor's telling you. So what we did is we basically have our own thermal well design here at JLab, and we use it almost exclusively in all of the systems that we design or we're involved with. And it basically, I'm going to show a picture, but basically it is a well that actually fits down into the cryogenic flow. And there's very good coupling between the flow and the sensor because we use basically a copper block that does this. And having it down inside the flow as opposed to having it on the outside of a pipe, which is one of the ways that it's done, allows us to get really accurate measurements. And I'm going to just zip to this picture real quick. What this thing looks like is it looks just like a regular well, except this well is sitting down inside of a cryogenic flow. We take these little standoffs and they have diodes mounted to them because we use temperature diodes for reading these cryogenic temperatures. And so we install those down in the bottom of this tube, okay, and we bring those wires out. And the first thing we do is, because if you think of this diode as sitting there inside of this cryogenic pipe, there's a couple of things going on. One is it's sensing the temperature of the fluid. The second thing that it senses, though, is where these wires turn around and go outside the box. Actually, those wires are a conductive tab that can bring heat into the cryogenic cold box where this is mounted. And it may only be a tiny amount of heat, but when you're dealing with temperatures down at like 2 Kelvin, this can make a huge difference. And so what we'll do is when we bring these wires in, the first thing we do is we come out and we put Stiecast around these tips right here, and we wrap 3 feet of this diode wire around that tip, and then we Stiecast it there. And what that does is it basically, any heat that's coming in from the outside world gets anchored to the process pipe temperature, because this thimble is really close to the temperature of the process. And so that's a real good intercept that prevents us from getting in any extra wattage coming down to this diode from that outside temperature source. And let's see. The other thing that we'll do in those instances where we're, for example, we're using the diodes down at very low temperatures, like in the 2 Kelvin range, as I talked about, is you can also get stray radiation effects from if the diode is mounted into a pipe and the open hole of that diode well is looking at a surface that is at a higher temperature. So this pipe is at 2 Kelvin, and let's say there's something here that's at maybe 80 Kelvin or even 300 Kelvin if it's the outside wall. Just the diode seeing that temperature can change the measurement. And we've seen that. And one of the things that we'll do in those instances is we actually build a little heat shield and put around the end of the diode well to block that temperature. And I'll give you an example. This is inside our 2 Kelvin cold box. And so this is one of our wells sticking up with the Stiecast on it. And what you'll see is this little copper shield is basically tied to the pipe. So this temperature of the inside of this is very close to the process pipe temperature. Yeah.
What about the long-term effect of ionizing radiation?
I couldn't understand.
Long-term effect of ionizing radiation.
Oh, now none of this equipment that I'm talking about right now is mounted in a high radiation area. Now that's a different problem, but a lot of these same things can be used to install those. A lot of people use things like Cernox, and there's some other sensors that we've used over the years in those types of environments. But the way to protect the outside world temperature from coming in is similar.
The solder joint that you make, have you had problems of it contributing to your temperature reading?
No, we actually haven't done any specific studies. You're asking about this right here.
Yeah.
Yes. To date, I have not seen any effects from that. If they are, they're small enough that we haven't noticed them. Now, these are not thermocouples. These are diodes. A thermocouple, you know, for everybody, a thermocouple basically is where two junctions come together of dissimilar metals. And at that junction, you can actually generate a slight voltage. And if your soldering techniques and the transition wire you're using are not exactly right, you can actually make your measurement incorrect by making those joints improper. But this is a diode anyway. So one of the things we do in our 2K cold box is we'll do things like this, and that's to prevent this diode from seeing any stray thermal fields from outside. And we've done this in multiple places and had very good luck with it. I'm not saying necessarily that you should do every one of these things. I'm thinking that if you're involved in a vendor's proposal analysis or something like that, these are some of the things that you think about when you're looking at stuff and say, well, does their proposal to work with these types of things make sense? Does it look like they're addressing these types of problems? That's really what you're saying. Another place, which seems like it would be a real no-brainer, but it does cause significant problems, and it depends on where you're trying to measure the pressures and at what level you're trying to measure the pressure. Are they high pressures or low pressures? But one of the areas we've seen issues with is in where the instrument tubing is connected. If you want to measure the process pressure inside of a pipe, let's say in a cryogenic system, you have to connect a tube to that pipe. And then that tube has to come through to the outside world so that you can connect it to some pressure transmitter. And a lot of times, what you've seen in the past is they will use either tubing that's really small, which tends to get plugged if you have any contaminants in the system. Remember, at the temperatures we're talking about, just about everything else on the planet is a solid. At 4 Kelvin and 2 Kelvin, there's not much that isn't a solid, if anything. So we try to look at things from the standpoint of we don't want the tubing plugged, and then there's also a few other little things that we have to look at. You obviously want to, like I said, size the tubing so that you don't, that you're not real sensitive to plugging. The second thing is that you want to make sure that your connections are very resistant to leaks, and that's especially critical in subatmospheric systems like our 2K system. And then also you want to try and design your tubing assembly so that they resist these things that are referred to as thermoacoustic oscillations. And I'll just kind of hit a couple things here. So we use only 0.25 inch tubing in all of our systems. Some of the older systems use smaller, like 3/16 or even in some places 1/8 inch tubing. And those tend to be problematic if you have any contaminants floating around in your system. They can actually plug those tubes up just like if you had dirt plugging them up. The other thing is that we typically on almost all of our systems, unless we have a real reason, we either weld a fitting or we would use VCO or VCR connections. In years past, it used to be very popular to use swaged compression type fittings. And in a helium system, we found that's a very bad idea. Typically, swaged fittings or compression fittings will last only 1 or 2 cycles, and then after that, they leak. And it's just a very bad idea to invest any money into that sort of technology. It's much better if you can weld it or put a VCO or a VCR fitting, which is designed to be broken and a new gasket put in, and you can put these things together as many times as you want. And that's especially important on obviously on the parts that come out of the cold box where you may be doing a lot of work on, like changing pressure transmitters or that sort of thing.
Jonathan, when you say swaged fitting,
Yes.
Are you saying that
Compression.
a couple of cycles, what you mean is a couple of cycles as in the system cycles or opening it and closing it?
Yeah, if you, let's say that you have a compression fitting on a pressure transmitter, and you come over to that fitting, and you loosen it up, and you
Okay.
put a new transmitter on, and you tighten it back up, or whatever you may be doing. After 1 or 2 cycles, the manufacturer says, we don't guarantee it anymore. And so you may have gone through a lot of leak checking and pressure testing and all that sort of stuff at the beginning of your run, only to find out years later you're actually losing a significant amount of helium through these connections.
I've looked at it the same way, and it's just a pressurization and depressurization cycle will also change the swage.
Yeah, yeah, I don't
Cause
disagree.
the leak.
Yeah, we don't like them, I don't use them, unless I have no choice.
It's good old technology.
Yeah, it's good old technology, that's a good way to say it. Just to kind of talk about TAOs a little bit, I don't know if people are familiar with this, but essentially if you think about this, what happens is you've got a pipe that's got cryogenic fluid in it, and you've got a tube that's connected to that cryogenic pipe. So on one end, the tube is at very cold temperature, and on the other end of the tube, it comes out of the cold box, which is at room temperature, okay? And what can happen on these tubing runs, if they're not done quite right, is you can actually have an oscillation that sets up in the tube, and it can kind of slowly bounce back and forth between the outside world and the inside of the cryogenic pipe. And where that will manifest itself sometimes is if you see systems where you have pressure fluctuations, where you're reading, instead of having a nice tight bandwidth on your pressure reading, you might have something that looks like this. And that's a form of this, potentially. You have to look at it to see if it's specifically that. But what will happen is basically you've got cold gas that enters the tube, it starts to come down the tube and it starts warming up. And as it warms up, it wants to expand. And so it changes the pressure in the tube, it raises it, which then tries to push it back out. And so you get this kind of burping action going on. And so it can actually set up a small oscillation that sits there and oscillates back and forth. And because the pressure transmitter is deadheaded on the end, it will see these pressure fluctuations in the tube. And so what will happen is, again, on the control system side, your measurements will not be 100% as tight as they could be. And if you're using them to control things like valve positions or speeds of something, you might see your PID loops oscillating to compensate for that sort of stuff. The other impact is on a lot of the big systems, it's not so critical, but it can actually set up a little heat pump, and it can actually bring in tenths or tens of watts from the outside world into the process piping, and it acts like a little pump that can bring these in. In the larger systems, it may not be so critical, but if you're dealing with a really small refrigerator that may is only made of 50 watts or 100 watts or something, you really got to pay attention to these sort of things. And so, basically what we do is we've found over the years that if you set up vertical loops, and one of the things Rob will talk about a lot, which he may have already mentioned, is that if you want to set up some sort of a buffer that prevents things from getting these types of oscillations, what you do is you set up these vertical loops. And what you're doing is you're setting up gradients, small gradients across this tubing, so that it prevents this oscillation from coming back and forth. And what that looks like is, I'll show you a picture of it in a second, but essentially what it does is it provides this mechanism for dampening this gradient oscillation. And what happens is these temperatures will kind of stratify out on these vertical runs of this tubing. And by using these coils that we do, it basically allows you to get in the vertical run height that you want, but in a small area. So you don't have to do them this way, but this is one of the ways we do that. And what this looks like is basically whenever we come out of the pipe, we immediately do these vertical loops real close to the pipe, and then we'll go off out to the PI port and come out of the cold box. And so if you were to turn these around and look at them, they're just basically loops just like this. And if you're building a piece of transfer line, you can do the same thing. We've actually wound them around the pipe before they come out. And we found this to be very effective at getting rid of these TAOs. And like I said, on some of our systems, we're subatmospheric, and so we may be reading like millibars or thousands of a millibar type changes. So we want the pressure oscillations to be as minimized as possible. What this looks like in real life is like that. This is a piece of 4-inch tubing that comes out of the pipe, and then it makes these vertical runs. We've used these successfully in a lot of different places and had very good luck with it. The other thing, which I'll talk about too, where we've seen problems over the years, is whenever people try to use a differential pressure transmitter to measure liquid level on a cryogenic system. A lot of times you'll see people in years past have tried to use it, they've kind of been unhappy with its performance. And there's reasons for that. And you have to plan into your job how to install these things in a way that will minimize the problems with measuring it. So if you want to measure like a dewar that's got liquid nitrogen in it, and you want to measure that liquid height, you can do it using a superconducting probe, or you can do it using a differential pressure measurement. Basically, you're measuring the pressure between the bottom of the dewar and the vapor space at the top. And so you'll run these tubes out and connect it to a differential pressure transmitter. But it's real critical how the bottom tube runs. And you have to pay, like I said, a lot of attention to that. And so one of the methods that we in our group have come up with to deal with this over the years is basically this. And so if you think about the dewar is sitting here with liquid in it, and you've got a tap at the bottom and a tap at the top. At the tap at the top, we'll have our standard vertical loops on it. But the tap at the bottom now, what you got to think about is there's liquid coming into this tube. And so what's happening right here is we will set up a system where we have some specific measurements of specific heights and specific distances where we will build the tubing like this. And this, I've drawn it this way, but in reality what we normally do is take these wands and we wind them around the vessel. So I'm kind of showing it weird right here, but essentially what you're trying to do is you're trying to control the meniscus point, the point where you're changing from liquid to a gas. Because what you don't want is you don't want the liquid shooting back and forth inside of this tube, causing oscillations on the pressure transmitter. And so what we do is we will put a braid right here that will go over to the vacuum shell. So we're providing like a real anchored high temperature point here. And then what happens is the liquid comes into this tube and starts to come down this way. Once it hits this higher temperature and it vaporizes, and what that does is it sets up kind of an equilibrium between these 2 points where you're setting your liquid point where it changes from a liquid to a gas. And by doing this, we're controlling it to be in this area right here between points 2 and 3. And by doing this, we have found we get very, very stable liquid levels in the dewars. We don't have this problem with oscillations that we've seen in other systems. On these, yes, we do. Actually, we have pressure transmitters, and we will use a calculation to come up with a more accurate reading. I'm just going to kind of go through these. You can look at the slides, and if y'all have questions later, you can call me and we can talk about it. Another place which seems like this would be, again, a real no-brainer, but we've seen this before, and in fact, this very thing happened at S&S with their main cold box. It was built by an external company, and we actually discussed this very subject about conductors in a vacuum. And when they brought the cold box there, when they first turned on the heaters inside of it, inside of a cold box there are filter beds inside of it. They're full of charcoal. There's beds at the 80 Kelvin level, and there's beds at the 20 Kelvin level. And what these beds do is, again, everything is a solid at the temperatures we work at. So these charcoal beds essentially filter out all of the non-healing contaminants that are inside the stream as it comes into the cold box. But you have to regenerate these beds periodically, so you heat them with heaters. So these things have big band heaters around them, and you turn on the heaters and you heat them up, and it cleans out this contaminants like oxygen or neon or whatever it might be. And what they did was they basically violated this rule. They did two things. One, they if you put conductors inside of a vacuum space, you have to use the right kind of insulation. And I know that sounds like a really stupid thing to have to say, but it's not uncommon for people to make that mistake. You have to use the right insulation. You cannot put plastic insulation or the normal kinds of thermoplastic that we normally use outside of the cold box, because these things will break down inside of the vacuum space over time. The second thing that you have to do is you have to remember in the vacuum, there's no air to take heat away from these wires. So if you undersize the heat wires, or you kind of just barely make the size, let's say it really should have been a 10, but you put in a 12. Here's where it will make a huge difference, because what will happen is the wiring gets really hot inside of the vacuum. And it literally, if the insulation is not the right type and you don't size the wire correctly, it'll burn the insulation off of the wires, and then everything shorts out inside the cold box, which is what happened. What happened there. And so what we do as a rule of thumb is we basically calculate what is the size conductor that we have to have, and we upsize it 1 or 2 sizes. You know, just upsize it, put in the bigger wire. It allows more area to try and dissipate that heat, so you don't get these buildup and heat concentrations that won't melt the wire. The other thing is you obviously want to use something that's like a glass insulation or Teflon in some cases, but you definitely don't want to use thermoplastic.
How do you check the wire on the job that you got the right wire?
You mean for a vendor or for something we're doing? If it's something we're doing, I know what it is. If it's something a vendor's doing, the only way you can do it is by telling them in writing what they have to use, which is what we do. And then when you go out to do your inspection of the equipment, when you're doing your acceptance, you need to check it and make sure.
The thing I've had to do a couple of times is in a vacuum, if your material is compressive, that means when you put a vacuum on it, it'll also expand.
Mm-hmm.
And if you go out and you find something and you compress it with your fingers,
Right.
and it really kind of compresses down 10%, something's wrong.
Yeah.
You got to get something that's really kind of hard.
Yeah, I agree with that. But we also, like I said, we'll use the glass insulated wire too, which is like a woven glass.
Yeah. And that's what I've found. I've found it 3 or 4 times now. That, oops, guys, go look at what you use here.
Yeah.
Or not. If you can push it down, the vacuum will tear it apart.
Yeah. Yep. Well, they tend to, especially if it's something that may have a lot of gas in it.
Yeah.
If it's a material that has a lot of gas in it, and put it in a vacuum, what's it going to do? It's going to blow up. So anyway, these are things that might sound like no-brainer kind of statements, but this is stuff that happens all the time. You have to look at it.
Back to your issue with measuring height of the liquid column.
Yep.
Do any of the normal process technologies, something other than basically a manometer? I was wondering, do you guys are you able to use anything like the acoustic or optical sensors for height?
That's something that we looked into a few years ago. I have not currently ever used one of those. I know exactly what you're talking about.
I've used
No, I've never
an
used
industrial
one.
process. I was curious if anybody had one that was,
I have not seen one that I'm not saying it doesn't exist, but I have not seen one for this type
I've
of
seen
use.
an ultrasound try it, but it puts too much energy into it.
Yeah, okay.
And it turns the liquid to gas.
They have a couple different brands. They have another one that uses the radar frequencies for doing that kind of thing. But somehow you have to keep the electronics outside the cold box and the thing that's doing the measuring inside the cold box. So I haven't looked at it.
Well, I've also used some that were basically like a fiber optic, and based on where along the length of the thing, the liquid went.
Yeah, there's lots of different ways. We also use superconducting probes, but each thing has its own baggage you got to take along with it. Superconducting probes are great, unless the pressure inside the vessel changes a lot. And if the pressure inside the vessel fluctuates quite a bit, and you get up to like 1.4, 1.5 atmospheres, your liquid level measurement can all of a sudden disappear. You have no liquid in there. It's because of the way that the actual probe is reacting to the pressure changes.
I've seen one on a hydrogen tank which looked like a tape. It was just on a
Yeah.
And they measured the change in the impedance.
Yeah, that's how the superconducting probes are made. You have basically a piece of superconducting wire that's hanging down inside the liquid. And as the liquid level comes up and down, it changes the
And
resistance
it
of the
wasn't
probe.
straight up and down, they wrapped it around the tank, so they had 500 feet of it on the tank.
Wow. I haven't
Yeah.
seen that.
So Jonathan, is it that you have to be careful with your insulation mainly because the wires in a vacuum get so much hotter?
Yeah, inside of a vacuum, any wires that are carrying a significant amount of current will heat up. And you have to plan your routing through the cold box, and you have to plan your insulation to take that into account. And like I said, it comes into play on our systems because we have beds inside of a cold box which have big heaters on them. And so you got to plan that. You don't want to run your wiring near anything that's critical, or you don't want to run it near your instrumentation. You don't want to wrap it around anything that might not react well to being heated. That's all. Again, when this happened at SNS, like I said, it burned up the wires, it burned up a bunch of the super insulation. We had, there was a fair amount of work to do to fix it. We knew something would happen because after they turned the heaters on, for a little while, the power control was all shorted out. We're like, what's going on here? And then that's when I went back and said, what kind of wire did y'all put in there? And that's when all this came around. Anyway. All right, just the last couple of slides. Ralph, I think, previously mentioned this. I'm just going to kind of hit on it one more time. But variable frequency drives, they're great. They're for speed control on AC motors, and we use them in a lot of different places in Cryogenic. Normally, the way these things are set up, you buy them, they're 0 to 60 hertz, and they may be up to 3,600 RPM type motors that you use these with. Our cold compressors actually operate up to 640, that's supposed to be hertz, but 640 hertz. And so they spin at very high speeds. And we noticed something that was very odd, or back during some work we were doing on SNS. And that is that normally, well, I'll just explain this real quick in case people, when I say a variable frequency drive, what I'm talking about is basically something that takes an AC sine wave, converts it to DC, and then basically reconverts it back into AC as this chopped kind of wave, and it varies both the magnitude and the frequency depending on what kind of VFD you want to change the speed of this motor. And so we'll use those on the cold compressors up to frequencies of like 640 hertz. And one of the things that we noticed is that everybody tells you that VFDs deliver really high power factors. That's for those of y'all that may have forgotten this or whatever. It's basically you're putting energy in, and it's basically a ratio of how much energy is actually being used to do work versus how much energy you're having to put in. So there's some overhead that you're giving up in heat or various loss mechanisms like that. But the kind of the belief out there is that when you put a VFD in a system, you have a really high power factor. It's like magic. But in reality, what we found is that, well, the high power factor basically exists from this line this way into the power system, but not this way into the motor. And so the power factor on this side can vary by quite a bit. And where that is critical to us was when we were doing our cold compressor runs. The cold compressors in our 2 Kelvin cold box, there's 5 of them. And in order to pump down, we were having to basically vary the speeds of individual cold compressors as we were going through this pump down from basically 1 atmosphere. A pump down is basically where we take the vapor space that's over the helium and we take it from 1 atmosphere all the way down to 0.039 atmospheres, which is 2 Kelvin. And what we were noticing was over the years is that in order to make this pump down successful, we were varying the speeds of these cold compressors to keep them away from their current trip points. And we had figured out, Rao had basically figured out how to make it work, but we never really knew why it was doing this until at SNS we were finally able to make some measurements. And one of the things we found out was that the power factors actually vary in this frequency space as we go from 0 up to like 600, 640. The power factor between the VFD and the motor is actually changing by a lot. And what was happening is as we were hitting these wells, the coal compressor is drawing more current than at these peaks. And so we were basically manipulating our pump down curves to try and get around this problem. And so what we would do is as one of the coal compressors would start nearing its trip point, we would slow it down a little and speed up another one that wasn't near its trip point. And so one of the things that we're really wanting to look into, which we just haven't to this point in time, is why is this? I talked to some people that build these VFDs, and I never could get any real good answers. I don't think they ever really looked at this, at least at the time that I was talking to them on the phone, because they weren't really, in most applications, you're not using the VFDs the way we do on the coal compressors, where you've got multiple rotating devices that are all chained together and operating as kind of like one unit. And so this is something that we were very interested in trying to get some more information on, because obviously if we could do our pump down with the power factor real high or constant through the whole pump down, we would have a lot less issues to deal with during our pump downs. It would be a lot smoother.
A couple of real quick questions.
I'll try it.
No wave modulation. You didn't try any wave modulation?
No, we didn't change any of that
You
in
didn't
the
shape the
VFDs.
wave?
Yeah, you can change the shape, you can change the frequency, and we did not do any of that. That's one of the areas we want to look at.
The second part, did you put off any radio frequencies that shut down the walkie-talkies and everything else in the area?
No, I haven't seen that with these. Now,
That's why you get the power.
yeah, well, VFDs will make horrendous noise. You can change the, what happens with a VFD is it has a carrier frequency, just like a radio station. And
The motors I put on an oil rig, we set them at a constant torque.
yeah,
And we shape the wave.
right.
And when you do that, you basically set the power factor in a power level. And then you just grind it out, and it sits right there, and the speed will vary to maintain that torque.
Right,
And the power factor stays level.
right.
But if you don't wave shape, you put out this radio frequency that'll set all of the radio frequencies in the area down.
Right.
Airplanes and
Yeah, I
everything
got you.
else. And
Yeah, one of the reasons we may not be able, I'm not saying we can't do that, but one of the things that we're sensitive to when our coal compressor train is basically, they're pumps. These things are pumps. And so as you speed up or slow down one of those pumps, it changes the flow through the whole system.
You're doing a mechanical engineer's delight. He's
Yeah.
got a compressor that he really wants a motor that runs his compressor like he wants to.
But like I said, it's like having 5 devices that are all chained together in one piece of pipe. And so you really have to be careful how you speed up and slow down individual stages, because the coal compressors are very sensitive to density changes at their inlet. And those are all sorts of things. I won't bore everybody with. If you're interested, we can talk about it. But anyway, so this is one of the areas that we were wanting to spend a little bit of time in to try and gather some more information. I will tell you that one other thing which is real interesting, a lot of people may have done this before. We just did this a few years ago for our CTF plant, and that is there's another little technology that's out there that's called a line regenerator. And basically what a line regenerator does is if you have a motor that's being used as a braking function, like a conveyor belt, or over at CTF we use brake motors to provide a load against an expander, a reciprocating expander. And so in that function, you're basically using the motor as a brake. And so what happens is, as the process is trying to brake this, it basically it supplies extra energy back here at the DC bus. So the voltage back here at the DC bus starts climbing because this acts like a generator. And what you can do is, if you go out and buy one of these devices called a line regenerator, it will look at, if you can connect it to this DC bus, and what it will do is as the bus voltage climbs, it'll siphon off that extra energy, convert it back into power, and put it back into the wall as an offset against the building power. And over at our CTF facility, we actually installed one of these devices, which is connected to 3 VFDs. It shares, there's a bus inside here where all of these share power. And so what happens is as these expanders are producing energy, basically the line regenerator takes that energy, converts it back into a 60 hertz sine wave, and then puts it back into a wall. And over there, basically those three expanders produce about 5 kilowatts of offset power if you were to look at it versus what it used to be on the building, which doesn't sound like a lot, but it's been running for like 24 hours a day, 7 days a week for, oh gosh, since maybe 2006. Yeah, in that range. And so, you know, this was kind of a cool project. I would like for us to see if we can do more of these types of things. Anyway, that's it for my talk. If anybody has any questions for me, you know, you can just call me or email me or.
Thank our
This
speaker
was
one more
very
time.
brief.
If there are no additional questions for John, then we turn over the floor over to Donnie, who will be talking about the design.
Okay, let's continue with where we left last time. It's kind of figure out how to design systems based on the thermodynamics, power efficiency, how to match it to our loads. But I want to go over a few fine details of before we start writing specifications. So we're all interested in, before we write down specifications, what's going to do with the cost drivers. Obviously, we all know it's the capacity. The bigger the more the capacity, we will cost it more. The other thing, what we do not pay attention to is the pressure rating. It comes in few different ways. One is there are places where we need very high pressure rating, like we have the Bureau liquefier for Bureau mines, we stack in the methane fail or the gas fail, where it has to be built for explosion proof, where all the controls, everything were like each and a half to 2 inch thick plates. Because it has to withstand an explosion if it happens. There, we definitely need that. But for example, in other places where, like I said at the beginning, component selections, at 20 atmospheres at 300 normal room temperature is normally allowed to use a 150 level flanges, like 150 pound flanges are rated up to 280 pounds or 20 atmospheres. But if you just cross that boundary, say for example 22 atmospheres which you have to choose, you are now stuck with a 300 pound flanges. So just because somebody is doing the cycle analysis, just he's only concentrating on his thermodynamics and not paying attention, which happened many times, like our CHL is designed for 22 atmospheres, because that added up so many extra heavy flanges on the system and it carries through. So people need to pay attention to, and also it affects the relief systems. So if you higher you put in, now we need again a margin so that if it design itself is like 21, 22 atmospheres, now you need another 2 atmospheres as a thing before the relief lifts. So this all will push the components higher and higher, and also makes it more prone to the maintenance issues and reliability issues. So that one of the things, I wasn't as cognizant of it when I was a vendor. But when I became a user, I started observing all these things which are driving the cost of the systems. So I thought it was worthwhile to point out to them. So system capacity and margin allocation. Well, it's important because we don't know every component to the finest detail. We always have to make sure the system is designed conservative. If we make it too conservative, it's going to be a system will have excess capacity and will waste the capital. And also it will run most of the time at off design, may not be at the best operating point. But if it is too small, the whole project may be in danger. So it's a balance. But at the same time, how much margin you need to put in and it all comes back to very careful. And that's where the kind of experience comes into picture, is how do you allocate these things. So specification should encourage. One of the things you can buy easily when I became the user, the vendor, is to see there are certain components of the system, like for example heat exchange. They make them in a block sizes, in a oven, they come in certain blocks. Even if you want a little smaller one, it's going to cost you as much or more sometimes, because to take something out of their standard block. But being bigger, yes, it may cost you more gold box size, but it will give you more capacity, margin, or able to make your system more tolerant to something else coming short. Anytime passive components like heat exchangers, bigger size will not bother as much as an active component. If you make a compressor bigger or turbine bigger, yeah, it can have a devastating effects. But a passive component like a pipe or a heat exchanger, being bigger is not as bad on the performance as an active component. So you need to write your specifications, encouraging vendors to make sure they are selecting towards a cost-effective higher side. They may not recognize this unless you bring it to the point and encourage them your design process and your specification. That's one of the things I learned when I became a user. I said, hey, why should I pay more if I allow them to pick more standard blocks where conservativeness is built in? Another thing is, like we said, we really don't know exactly our loads. We'll be kidding if we say we know exactly what our load is. It changes every minute. Depends on outside temperature. Depends on the vacuum in R42 cryomodules, or the transfer line, or the cans. Everything has an impact on the energy of the beam they want. They're all varying constantly. Nothing is given. Although we say, yeah, we want the system designed for one thing. That's a myth. That's one design point to simplify it so that we can measure or something we feel comfortable about acquiring a plant. But that's where we sold a lot of plants, we bought a lot of plants. But this is what we typically started doing, like I said, from when I became a user from SSC days onwards, is to specify the maximum system capacity. That's what you need to do more than your normal operating. Get the plant like cool downs, transients, all these things to take into account. Will normally be higher, including a margin in it. Then you have to specify where you want to operate normally, so that the vendor really looked at that point to how he is going to operate there. Then you want to look at 100% liquefaction, 100% refrigeration, and 50-50, and also the turn down. These are the 6 we strongly recommend when you specify a helium liquefier, to make sure they are understood upfront before you buy it. Because let's face it, there are not, to my knowledge, there is no one plant operating as specified or has a capacity asked for 100% of the plant. There is no plant there. If you take Brookhaven, it's designed for Isabel project for 3 times the capacity where it is operating for rate. Okay? We bought ESR from Berkeley, it's designed for some other experiment. Okay? So everything, they move around, they're designed. But if you did this, then even if you swap for a given Carnot capacity, they're very much interchangeable. And if you looked at it at the front of the design level, the implications are not that strong on the cost. Its question is how they are arranged is more, and people can take advantage in the components they are using. If it is not specified, like I said, we have one of the pipes was small in the SNS refrigerator on the cold end. It's just a piece of pipe. It's limiting the 4K refrigeration, because that's one of the specification. I mean, in the specification, we did not specify that mode of operation. So, and what are the various factors which lead into these uncertainties? One is uncertainty load estimates. We all know, we are guessing what's the transfer line heat leakage, what the cryomodule stack heat leakage, all those that distribution loads. And control, to control the system at capacity, people, I haven't seen people consciously thinking what it costs the controls itself will take to keep the system stable. That's in most of the plants I observed, it's taking around 4% when they're finely tuned, and then you got uncertainty instrumentation that costs you around 1% because you don't know exactly where that is going. Then degradation, like for example, I told you on the bypass valves on the compressors, we put in 6 megawatts of CHL, and when cold box is not running, all the 6 megawatts are consumed on the bypass valves. They can cost you the full power, and those develop leaks over time because they're constantly working. And we won't be rebuilding, probably we get a chance every 10 years, maybe every 8 years. So we have to design our system so that allowing the certain amount of leakage is going to happen, and then it's taken into account up front in the design. These are the factors, I mean, when you're specifying, unless you have an operational experience. I'm the first one to admit, when I was a vendor, I didn't recognize a lot of these things. Learned as I became a user. And that's why I'm trying to bring it up, so that as the users, we need to feedback into the vendors to make sure this is addressed. Because for them, they say, okay, you want a 4 kilowatt plant? We'll give you 4 kilowatt. They won't care all this. What the 4 kilowatt contains, we as the users have to specify and make sure these are all taken into account and make sure they're addressed. And another thing is the cool down. Yeah, we always say steady state. Oh, yes, steady state. We need to get there. How do we get there? Like Harley Magnet, we have a refrigerator. I'm not sure we're going to get there without some additional help to get cool down help. Things like that. There are certain issues you need to address up front. You got to have different plans. And some of them are going to fail. You will have a turbine failure, or you will have a valve leak or something. And you can't take the whole experiment down because it's going to cost a lot more. You have to allocate some critical failures and be able to meet a certain minimum operating, and all has to be addressed. Every critical component, we normally try to look, okay, what happens if this fails? Where are we going to operate before we have a maintenance, something we can do? So these are all we try to look this many angles now because of the experience we got as the users, and that's what we want to bring it up. So in general, all these add up, at least 50%. That's why the refrigerator is bought, say if you have a 3 kilowatt, they're bought for 4.5 kilowatts. Now, you have a 4.5 kilowatt machine, once everything is stored and operating, you only have 3 kilowatt load, even if everything is added up exactly what plant. So where is it running? It's running at 2/3 of the. So now most of the plants in the olden days were set to use the full power capacity. Now with the floating pressure, we don't use all the power, but if it is designed with all those 6 components in mind, modes in mind, then it will automatically go there with proportional reduction in power. So that is the importance of the floating pressure and able to allow the plant to seek its own operating position with the maximum efficiency. So then is the relief system. Again, we need to make sure all the reliefs are coordinated with certain failures in mind and prioritize it so that what is a systematic subsystem failures to. So this is what we did for SNS, and that's what we're doing for the 12 job, is to make sure everything is an integrated planned relief system with a certain amount of delta overhead between relief, lifting, and operating point. The higher the delta, you will have the less helium gain. So when we designed the SNS, with the industrial standard where we came from, with our background, we lose only like 1/10 of what we lose here in the helium. And so, not even 1/10, probably 1/20th. They lose half a tube trailer versus we lose 3 a month, every 3 weeks, yeah. So, I mean, there's a substantial difference in helium usage when it is designed with those margins appropriately addressed, when all this is stacked appropriately, and all your utilities will come down with it. So, relief pressure and shutdown of the each subsystem and total system shutdown, power outages, and you have no control of when utilities fail. So the goal of the relief system first is to protect the personnel, equipment, and then the helium loss. So that's how you hierarchy. Like when we had Isabel, we lost all the helium, but we don't want anybody or any equipment damage. Those are the high priorities. And the next is the verification and acceptance test. Quite a few things, like I said, I learned when I became a user. This is one of the things, yeah.
Rob, can I ask a question?
Yeah, sure.
On your release,
Yeah.
so of course, proper sizing during upset conditions is very important.
What's that?
The proper sizing during upset conditions is very important.
Yeah.
You're talking about using helium on a continuous basis. Are you saying that the way the release is designed or incorporated in the system affects your normal helium loss during operations?
No. What happened to say, let's take CHL1 of our existing system where we are. The reliefs are distributed like there are 15 pounds, 20 pounds. They're all over from anywhere from 10 pounds to 300 pounds. Whereas SNS, we classified as certain groups, and we made sure there is enough overhead between normal operation and delta. Here there are reliefs are much closer in a lot of cases. Set point to the operating condition. That is basically which drives the leak, because if you are operating very close to where it relieves, all the springs with the time they move. They're not really holding exactly the day you install it, and it's very hard to keep track of that many, especially thermal reliefs all over. So you want to keep enough margin, especially for thermal reliefs and SNS. You said, doesn't matter, we're going to make it very high class, high level, so they won't be anywhere close, because thermal reliefs doesn't need to be there. So when you select the components and rate it like that and leave yourself a bigger margin, we allowed for these things to with time to drift and don't cause you like helium leak. Did I answer?
Yeah,
Okay.
absolutely.
Okay.
So Ralph, is
Yeah.
it proper to say that you're not really getting helium leak, you're getting relief too soon? You're
That is
getting
a leak.
relief when you don't need it.
It's English selection of wording. It's still a helium blast.
I guess the better way of saying it is that instead of
Designing it to the pressure rating of piping or vessel like that, a lot of cases people are setting the relief pressures for just above the normal operating conditions.
Much closer. Then, see, when you come up with a group and classification levels, like one thing what I try to do here is like, let's say 150 class, 300 class, some different classes. So even if it doesn't matter, the pipe we use, even Schedule 5, will take those classes. Why do you rate it low just because your process is sized at that? Should not be the only thing dictating the relief set points. That's how, like an industry, they don't do that. They go to the classes of rating. In labs, they don't follow the industrial standards, and okay, they think every 10 pounds is going to cost. There are very few cases where relief set point has a strong influence on the cost. They are very, very few because the equipment, the components have much higher rating, but we don't harvest it. We just derate them and let it causes problems. Okay, other thing is, this another thing I learned here is we didn't have test plans put into the equipment. Like when we bought CHL1, there was no way to prove what it does until the only test we have is the final when it produces 4.6 kilowatts at 2K. We didn't have 4K plant, we have problems on compressor, we have problems on 4K box, we have problems on 2K. Since we didn't have a test plan, we didn't know where to start, what component to start. So we started changing a lot of components. First they changed the compressors, and the heat exchangers was one of the main shortage in the cold box, but I know it's very difficult to change them. Then we changed modified the cold box, we added additional heat exchanger. It became extremely difficult to put our finger on which is the main component which is in shortage because there are no equipment for testing to figure out these things. So having an integrated test plan, this is what we did for SNS and what we are planning for our 1202. Even to separate out the cold box, the compressors, and everything subsystem, so we can prove where the problem is arising. And they will verify the vendor supplied equipment and performance operate at partial loads, also easier. Occasionally when we change some components, we can recheck it, the system capacity. And the transients are easy to handle. And so it doesn't cost as much, probably less than 0.5% or whatever, but it's worth the investment. And it proved, especially proved when we commissioned CHL1. The price we paid is too huge by not having the capability. So we try to encourage the test equipment. And the next one is, what are the lessons we learned over the years in building these plants? A great deal we can learn from operating systems. That's how I learned. More than as a vendor, I learned a lot more as an operating system today. Because you start seeing the implications, then you start seeing the theory behind it, why and why not, and see where they can meet. system. They can be good, bad. Again, I mean, sometimes, face it, some of these we wish we didn't ignore those things that we thought about more carefully. Analyze the data carefully before you reach a conclusion. This is another thing most of us do. We jump to a conclusion before we really understand it. And too often, perception of the problem is different or even very, very different from the realities. Believe me, it happens way too many times in my experience that what we jump into conclusion versus what actually is. Take your time, analyze it, and make sure you build in the proper analytical tools to make that experiment what is required before you say, I'm going to change this compressor, I'm going to change that. And they're all expensive. They cost you time and money. So, and new projects, I mean, success of the project depends upon organization. I mean, if you don't organize properly, cost estimate, and schedule planning and project execution, and make sure all the components of the subsystems required are included in the project. There are quite a few projects we normally forget one or two subsystems, and now everybody is running over budget and we're struggling to see how we get those, and it happens in almost every project. So you got to take time when you're planning a project to make sure everything is required is taken and are addressed. So, for example, on compressors, of course, we think we got under control oil removal, but most of the plants, probably more than half out there, have oil carried over into the cold boxes. That's not funny. I mean, that's really painful when oil gets into the cold box to clean it because it plugs the heat exchangers, and it really causes havoc. And improper frame size selection. We replaced all our compressors at CHL1 because of the sizes were not appropriate, and the number of stages. And we have 2 stages for a pressure ratio of 22, and that's not the optimum. We pay more than operating power because of how the size is selected. And the cold box design. What are the things? So it happened shortcomings. Most of them, if you design on a single mode, and there's no one mode for these cold boxes. You have to cool down a load, you have to warm up, you have to have failures. You may not use the, like you said, the cold box for the intended purpose. The project might have changed. So you have to, if you're going to put this much power in, make sure it's capable of delivering refrigeration to whatever the mode they're eventually going to use, just not the mode you're only envisioning for your experiment, because the delta cost is normally very small by designing it in an overall balanced plan. And undersized surface areas in the heat exchangers and high pressure drops, and overestimated turbine efficiencies, inadequate cool down lines. These are all we are living with now on CHL1. I mean, these are all I learned from most of it from CHL1. We have oil contamination, and we need to clean it. And in the 2K box, where our heat exchanger wasn't big enough, and the cold compressor efficiencies were more optimally predicted than they are, and the torque, like what Jonathan explained, none of us understood the torque versus. I mean, of course, power factor and torque are related. I mean, they are proportional, but we didn't understand the power factor on the variable frequency drives and their influence on the 60 hertz. One of the things is so difficult on these cold compressors is because there are 4 or 5 of them in series, and they all need to be a very delicate surge curves of each compressor. So when you have to work on one power factor of one compressor versus when your other ones have this, I mean, when you have this map, everyone can have the power factor influence, surge curve influence. It's a very complex map. And separating that out and navigating ourselves through this very torturous, I mean, it's a forest. You can't see any light because it can be power factor or it can be surge curve which is tripping you on any one of the 5 in series. So it's extremely difficult to put your finger on and say, this is where I need to correct it, even to separate it out. That's one of the things we faced a lot of time to sort that out. Although, if it is a single one, yes, I can see we could have separated much easily. Because there are 5 in series and the surge curves are on the top, it was extremely difficult for us to separate it out. Like, helium purifiers is another thing. Of course, we are probably fortunate ones here. Most of the installations or labs don't have any proper purifiers. and they take a lot of regeneration. And also, another thing is we found this when we had, I think 86 or, no, 96, I think, we had a power price, and they couldn't deliver the nitrogen. When we went to the NASA and we borrowed the nitrogen from them, that's when we installed a second door. So, helium storage, well, we saw the effect of big door more than what we wanted. We couldn't operate it because a 1% change in the door was almost swallowing the whole helium tube trailer, and our people, oh, it's not even 1%. We might have lost another 6,000 liters or something, and it's so hard if your helium door is too big compared to your usage and things like that. To track of your helium losses was very difficult. And also the door was not functioning properly, and so we could never use that big door, so we got rid of it. And specification included calorimeters, and another thing is it didn't have a way to really get the liquid out. It has only way to put the liquid in. And how much warm gas versus liquid storage has to be properly thought through, because warm storage costs you a lot more than the liquid storage, but liquid storage is required. You need a refrigerator to keep the liquid storage active. So you need to have your balance in your thinking based on your operational needs. What percent of need thing to be in which form. And the distribution systems, yeah, that's another thing is we underestimated our Bannet heat loads and everything. It's a lot more, I think, factor of 2 or 3 more than what was originally planned on our distribution system from the tunnel. And some of the problem areas what Jonathan went through on the instrumentation. So, some of the areas of interest for what are the areas we are working on, what we are interested in. As we go through this, one of these is, like we said, is the floating pressure, where it took a lot of our pain out of it by changing modes or operating modes. Once we figured out it can go from liquefied to refrigerated to reduced capacity very efficiently. And I'm sure there is a lot more can be done as next generation people take over and do that work. Then the screw compressor is another one. Like I said, even CHL2, we are designing, we are very proud, we are designing to be around 30% carbon. That means 70% is lost. So cold box is losing another 20-25%, and 45 to 50% is lost in the compressor. And that's one area which is not very sexy, and nobody is paying attention to, where we lose half of our input power right at the start of the game. And that's one area where we have some interest, and we are trying to make some inroads into it, and Pete is working on his PhD thesis towards that, to work on that area to see what we can do to improve that law, reduce those losses. And vanity growth, this is another thing. Yeah, this is very convenient for us to decouple a cold load from the warm and all these, and we're using so many banners all over. And before I came to the lab side, on industrial side, we minimize the banners, like what is the minimum, like only 1 or 2 between the refrigerator and the door, and we don't use banners anywhere else. But here, because of the loads are so distributed, and they need to be taken out and put back in service cold, we need these banners with isolatable valves and all. Because of that thing, the clearances have to be larger than industrial standard, because industrial standard banners are normally connected and disconnected at room temperature, and so they are a lot more tighter tolerance banners they use. And but they are contributing a lot more, and we started some program to analyze it, but we really haven't taken it to a final conclusion stage where we had to bring that program back on. Kelly had one student worked on it with Kelly, and but we really haven't have a continuation of work on that part of the thing. And another interest is the mass flow meter. We always want to know what's the load and what it is, and it's very hard to measure supply 3 atmosphere. That's extremely difficult to measure the supply flow. And we can't afford to measure the return flow because of the pressure drop. So there is some ideas we had, but we never really took it into practice to build any of these. That's another area. And software models to make these systems a lot more, less required people, and let the computers take over more and more. That's another area of interest we have. And expanders. Basically, I mean, we depend on turbo expanders from the across the pond for the helium service. I mean, we try to develop when we are in industry, rotoflow and Morphic range, but really, and that is now rotoflow is taken over by GE. They showed some interest, but nobody is really serious because the market is so small. But eventually, I mean, there has to be some amount of investment on this side of the pond to push the technology, so we don't have to depend on the other side of the pond for turbo. Of course, we have recipe engines, so Sam Collins vintage, but I have some ideas about how to take an automobile engine or whatever from the warm and drive and couple with a cold and drive, but like I said, we never really had time. These are the areas of high efficiency small refrigerators. Like we say, if the machine is small and everything, there are a lot more applications will develop, like sensors and all these things, like water security. There's so much interest for all these things, but the cryogenic equipment is inherently so large and so cumbersome to maintain. It itself is prohibiting from other areas of development. And the other is the driver development. So at JLab, this is where CTF is here, and we want to take it here at the 2K. That's what next talk Pete Converson is going to talk about from his master's thesis, how he did. And CHL1, the 6 GeV is going to operate here around 1300 watts per watt, whereas CHL2 will be around 900 watt per watt. So that's what our contribution in the R&D area at the large plants, and the small plants will be here. And this is what we think we should be able to map it down and bring the watt per watt instead of 300 watts, 2K watt wall plug power at CTF, and 1300 watts per watt at CHL1 to 900 watts per watt at CHL2. And P goal is to get around 2 kilowatts per watt on small systems. So this is the areas we are working on. So conclusions. So like I said, carefully develop requirements. You heard what's the theory, what are the various drivers, what are the various things you want to, as a user, you want to pay attention to, and make sure that the design goals are carried. See, another thing is, yeah, we read the specification, and the vendor builds it, and the cold box comes over, and it doesn't work. Because there has to be a systematic approach by the heat exchanger, and by the what are the tests they have done, and how can you use the test to make sure it's going to perform, or what did you specify in your specs to supply, and did you verify it? A lot of times we write specs, but we don't go back and verify, did they meet all that? We count on vendor meeting all that. That's too much of a trust which they haven't lived up to, including myself. So, and if the user has a lot of times we say, hey, let me put it there, the vendor will figure it out. If we don't know for the complexity of things what we want, if we can't envision it, don't think that. If the user has a difficulty defining the requirements or how to achieve them in the specification, then it certainly cannot be assumed the vendor will be able to provide them. Then you are just leaving everything to the fate. It's not to science anymore, it's just the hope it will happen. Okay. Well, this is where we started. What is an optimum system? Is it minimum operating cost, minimum capital, minimum maintenance, maximum system capacity, maximum available, a combination or some other factor? So, my idea is this is, hopefully this information presented gave you some idea of how to specify if you are buying a system and how to operate if you have a system at all. And floating pressure cycle is a step to get you that close to that optimum operating conditions or design phase. The main thing, central theme of this class is to minimize the utilities, so that for what you are doing, I myself don't know exactly the physics side of it and its implications, but we want to provide you what exactly you need, but where we can do is what is the minimum it should take to provide you that utility. And that's the main goal of our group. Save of natural resources. So, I hope you saw you need to understand the fundamentals to really specify or understand these things. So, we need to treat natural resources, not as an inheritance from our parents, but we are borrowing from our children and we need to give it back to them. We just can't use everything and say, hey, we used it up like our social security, we keep paying it. Okay. This is, like I said, everybody have a different idea of what an optimum system is, depending upon who is looking at it. And the optimum system encompasses everybody and everything. So, we like to see how take personal interest in how to use the precious commodity energy in accomplishing the end goal of the scientific needs. And it helped me a lot. A lot of people reviewed these manuscripts and everything, and so I thank everyone. So that's basically this 5 minutes course of it's all about.
Any additional questions for our speaker?
Yeah. What's that? Yeah, you can use, but question is when you size a cycle, see what sets is, what is the code box or the compressors, all these things which determine. We're not talking the code requirements, we're talking when you select these components, you have the choice to select higher pressure, higher flow. This is total energy supplied to the code box, exactly we call it availability, is a product of the flow and the pressure. And when you choose that pressure, make sure you're not pushing to the next class where you could address with a little more flow. You would have been a lot more economical in the design. I'm not talking about what class or what codes you need to meet. That's a different thing altogether. But you can, in designing the process itself, you have to be aware of these combinations of, not to push over certain boundaries of these codes where, by mistake, you happen to be in the bottom and paying for higher price. Really, you can do a lot better off by being on the other side of the border. Between 150-pound class up to 20 atmosphere designs and going to 22, you could have done 20 atmosphere with 10% more mass flow. You would have been a lot better off pushing it to 22 atmosphere at 10% less flow. That's what I'm trying to say.
Okay, I have 2 reminders.